Alright, so this one's a bunch of buffer problems, starting with number 4. Buffer solution contains a ratio of weak base to conjugate acid of 1.5. Calculate the pH of the solution of the pKa is 5.2. So make sure you get your equation sheet in front. You can use the Henderson-Hasselbalch equation to find the pH. pH is equal to the pKa plus the ratio of the base to the acid concentrations right here. And so pH is equal to 5.2 because that's the pKa plus the log of the base over acid concentration, which is 1.5. And the log of 1.5 is 0.17, and then add that to the 5.2, and we end up with 5.37 is the pH. Second one, buffer contains a ratio of 4.5. and then it is a pKa of 7.2. So pH is equal to 7.2 plus the log of the 4.5, and the 7.2 plus the log of 4.5 is 0.65, and adding those two together you get 7.85. So there's just some straight analysis of using the Henderson-Hasselbalch equation, and of course you get this equation sheet on the test. And then over here, some buffer extra problems right here. Which of the following is not a buffer system? A solution containing roughly equal concentrations of. Okay, and so a buffer solution, remember, has to be a weak acid or a weak base, and its conjugate base, or in this case, the conjugate acid right here. And so if you look through here, this is a weak acid right here, hydrofluoric acid, and its conjugate base, so that will be a buffer system. The bromide ion and the hydrobromic acid, and we know that hydrobromic acid is a strong acid, so it does not fit this criteria of a weak acid, so that will not be a buffer system. Phosphate and hydrogen phosphate, well, that is definitely weak and weak, so it can be a buffer system, and the hydrogen phosphate is HPO4 minus 2, and then the phosphate ion would be PO4 minus 3, and that would make a good buffer system because we have one that has one more hydrogen and one that has one less hydrogen. Carbonic acid and hydrogen carbonate, same thing, it would be a weak and a weak, and phosphoric acid and dihydrogen phosphate would be the H3PO4 and then the H2PO4 minus, once again, one more hydrogen, one less hydrogen, a good buffer system because they're both weak. And number 2, which of the following can be mixed together to produce a buffer solution? So remember, you have to have a weak acid and its conjugate base, or a weak base and its conjugate acid. The best choice is number B right here because we have H3PO4, and we have some Na plus that's going to spectate along with the H2PO4 minus right here. And notice this is a weak acid and its conjugate base right here. Alright, a couple more calculations of buffers right here. Calculate the pH of a solution that is 0.3 molar in ammonia and 0.2 molar in ammonium chloride. And then they give us the Ka of the ammonium ion right here, which is going to the acid in the buffer solution. So our buffer solution contains this ammonium right here. There's the chloride ion in there that will just spectate because that came from a strong acid, ammonium chloride. And then we have the regular ammonia right here that is 0.3 molar. So we're 0.2 molar in this. So looking at your equation sheet, to find the pH of this buffer solution, pH is equal to the negative logarithm of the Ka, which is 5.62 times 10 to the negative 10th, plus the log of base over acid. My base is the ammonium right here, 0.3, over the acid, which is 0.2. And I'm going to take and put this one completely into the calculator to show you how that goes. And so we'll do 0.3 divided by 0.2, enter, and then we'll do the log of that answer. So that's this thing right here, which is 0.176, and then I'll add that to this thing. But first, I'm going to do it without doing it all at once. So negative log of 5.62, enter exponent, negative 10th, and so this gives me 9.25, and then I'll add those two together, so plus 0.176, and I get 9.43 as my pH of that buffer system. Second one is exactly the same, but now we're given hydrogen fluoride right here, or hydrofluoric acid. And then we have the fluoride anion. So we have HF concentration of 0.3, and we have the F minus concentration of 0.4. And then we have the HA, or the Ka right here. And so the pH would be equal to the negative logarithm of this is 7.2 times 10 to the negative fourth, plus the log of the base over the acid. This is my base, so 0.4 over my acid, which is 0.3. So let's do this part first. 0.4 divided by 0.3 is going to give me 1.333, and then let's log that. And so this part right here gives me the answer of 0.125, just rounding. And then I'll do this part, negative log of 7.2 into exponent negative 4, and I get 3.14. Add that to the 0.125, enter, and I get the pH then equaling to 3.27. 3.27. All right.